Very good evening. So today we are going to discuss the alpha disintegration energy. This is a most important thing we need to understand. So already I explained what is meant to alpha decay, and here the alpha disintegration energy is the energy released during the alpha decay is known as alpha disintegration energy. The energy released during alpha decay is known as alpha disintegration energy. Is it visible? Is it visible to all of you?
Yes,
I
sir.
request one. Okay, thank you. So this is the basic definition of alpha disintegration energy. The energy released during alpha decay is known as alpha disintegration energy. So now, at the time of alpha emission, the emitting radioactive nucleus is normally at rest, having zero momentum. Hence, the total momentum of the final product in alpha decay must be zero. So the alpha decay of a nucleus, the alpha decay of the nucleus X, X is the nucleus of mass number A and atomic number Z and atomic number Z can be written like this, can be written as X of Z to A gives rise to Y of Z minus 2 to A minus 4 plus helium 2 to 4, and this is called as an alpha particle. Helium 2 to 4 is called an alpha particle. And here Y is called a residual nucleus. Y is called residual nucleus, and its atomic number is Z minus 2 and mass number is A minus 4 of atomic number Z minus 2 and mass number A minus 4. Y is called the residual nucleus and its atomic number is Z minus 2 and mass number is A minus 4. So if the residual nucleus of mass, and this also called as Y is also called as the daughter element. X is called as the parent element, a parent nucleus, and Y is called the daughter nucleus. So if the residual nucleus of the residual nucleus of mass MD. MD is actually nothing but mass of the daughter element or mass of the daughter nucleus, and since this is called the residual nucleus, therefore I can denote MD. And as the velocity and its velocity is as velocity Vd. Vd is the velocity of the daughter element or velocity of the residual nucleus. M alpha be the mass of alpha particle and V alpha be its velocity. M alpha be the mass of the alpha particle and V alpha be the velocity of the alpha particle. So then if you apply law of conservation of momentum, according to law of conservation of momentum, law of conservation of momentum. So the law of conservation of momentum says the initial momentum is equal to the final momentum. Initial momentum is equal to final momentum. Initially at rest, therefore its initial momentum is 0 and its final momentum is the mass of the residual nucleus into its velocity plus the mass of the alpha particle into its velocity. So 0 is equal to md vd plus m alpha v alpha, or m alpha v alpha is equal to minus md vd. Say this is equation number 1. Now apply the principle of conservation of mass energy or law of conservation of mass energy according to law of conservation of mass energy. So the law of conservation of mass energy says the total energy remains same, or the energy can either be created nor be destroyed, but can be changed from one form to another form. So here, if you apply law of conservation of mass energy, so this is the mass of the parent atom into its velocity square according to Einstein. That's equal to mass of the daughter into its velocity, mass of the daughter nucleus into velocity, plus the mass of the alpha particle into velocity plus Q. This Q is called the energy released in this reaction, or Q is the energy released in alpha decay. But our job is to find out what is the value of Q. Our job here is to find out the value of Q. Q is called disintegration energy. Disintegration energy. So now we have to find out what is the disintegration of energy here. Is it visible to all of you? Hello? Is it visible to all of you? Okay. So here, the sum of the kinetic energy of the alpha particle and the nucleus is called alpha disintegration energy. Therefore, disintegration energy Q is equal to kinetic energy of the residual nucleus and the kinetic energy of the alpha particle. What is the kinetic energy of the residual nucleus? Of md vd square plus of m alpha v alpha square. And we know from the equation 1, what is the equation 1? So capital MD VD is equal to minus M alpha V alpha, or M alpha V alpha is equal to minus MD VD. So from this equation, VD is equal to minus M alpha V alpha divided by capital M into D. If you substitute this value of VD in this equation, equation number 2, equation 2 becomes Q is equal to of MD, VD is minus m alpha V alpha divided by md whole square plus of m alpha V alpha square, or Q is equal to of. So if you simplify this, so in the numerator here we have md divided by md square, that gets cancelled, get of m alpha square V alpha square divided by capital md plus of m alpha V alpha square. So you just take the common. So of m alpha V alpha square is common, of m alpha V alpha square is common. So then, so you'll get m alpha divided by capital MD plus 1. Mass of the alpha particle divided by mass of the residual nucleus plus 1. And we know this half m alpha V alpha square is called the kinetic energy of the alpha particle. Kinetic energy of alpha particle. So that I can written like this: E alpha. E alpha is equal to of m alpha V alpha square is called kinetic energy of the alpha particle. Kinetic energy of alpha particle. So kinetic energy of the alpha particle. So then this can be written as Q is equal to E alpha into mass of the alpha particle divided by mass of the residual nucleus plus 1. And we know when you look at the equation, the mass of the alpha particle divided by mass of the daughter element. So this becomes A, this is A minus 4, this is the mass of the alpha particle, sorry, Q is equal to E alpha into, so you know mass of the alpha particle is 4, mass of the residual nucleus is A minus 4, mass of the residual nucleus is A minus 4. So if you substitute 4 divided by A minus 4 plus 1, so this gives rise to Q is equal to E alpha into 4 plus A minus 4 divided by A minus 4. So here 4 gets cancelled. Q is equal to E alpha into A divided by A minus 4. So this is called alpha disintegration energy. This is called alpha disintegration energy, where E alpha is kinetic energy of the alpha particle, A is the mass of the parent atom, and if you know the mass of the parent atom, then we can easily calculate the disintegration energy in an alpha decay. This is most important and frequently asking question in the examination. Please concentrate on this. So we'll move on to the next very important concept is the range of alpha particles. We know that alpha particles are really absorbed in matter. That means when an alpha particle is allowed to pass through matter, it is absorbed. They can pass through a very thin foil of mica or aluminum, but if you place the thin foil of aluminum or mica one over the other, that means if you pile the mica sheets one over the other, the alpha particle it's very difficult to pass through it. So now here we have to understand what is meant by range of the alpha particle. The simple and basic definition of the alpha particle is the range of the alpha particle is the distance through which an alpha particle travels before its energy falls the ionization potential of the gas is called range of the alpha particle. And the range of the alpha particle depends on the initial velocity or initial energy and the ionization potential of the gas the pressure of the gas, the nature of the gas through which they pass, the nature of the radioactive element also. So that is a basic requisite of the range of the alpha particles. Now, Grigor and Nuttall derived an empirical relation between the range of the alpha particles and the decay constant. So that law is called as Grigor-Nuttall law. So now we are going to we will switch on to the Grigor-Nuttall law. So the Grigor-Nuttall law says the radioactive decay element is directly proportional to the range of the alpha particle. So Grigor-Nuttall law. So in 1911, Grigor and Nuttall discovered an empirical relationship between the ranges of the alpha particle and the disintegration constant of the naturally active substance emptying them, and this is known as Grigor-Nuttall law. So let me write the basic statement of Grigor-Nuttall law. So Grigor and Nuttall discovered an empirical relation relationship between the range of the alpha particle and the disintegration constant or decay constant. Of the naturally alpha active substance emptying with them. This is known as Grigor-Nuttall law. So if you consider, let R be the range of alpha particle and lambda be the decay constant. So then according to the Grigor-Nuttall law, log lambda is equal to A plus B log R. So here A and B are the constant for a given radioactive series. You might have heard various radioactive series like actinium series, thorium series, plutonium series, so on. And here A and B are the constants of given radioactive series. A and B are constants for given radioactive series. So this A and B value varies from series to series, and the constant B is the same for all series, while the A is different for different series. So the constant B is same. This is B is same for all series, and A varies from series to series. A is different for different series. Different for different series. So this equation is similar to that of equation of a straight line. You know, equation of straight line is y is equal to mx plus c. M is the slope, c is the intercept, and here the a is the intercept. A is the intercept. So now the value of log lambda are plotted against the log r. That means if you plot the graph of log lambda versus log r, if you plot the graph of log lambda versus log r, so you will get the different series, different straight lines. Different straight lines are the, so this is a plutonium series. Plutonium series. Then this is thorium series. Actinium series. Now, if you find these three series, if you plot a graph of log lambda versus log r, you will get a straight line for different series, and you see the slope of all these straight lines are same, but the intercept on the y-axis are different. So that's what a is different. A is different for different series. See, this is the intercept for plutonium series, and this is an intercept for this is an intercept for thorium series, and this is an intercept for actinium series. That means the intercept. What is the intercept here? A is different for different series, but B is same for all series. B is what? The slope. Slope is same for all series, whereas the intercept is different for different series. So then, according to the Grigor law, I'll switch on to the next page. With the value of log, now we have plotted the value of log lambda versus log r. You will get a different series, and according to Grigor law, the range of alpha particle is directly proportional to V alpha cube. V alpha cube, where V alpha is velocity of the alpha particle. The range of alpha particle is directly proportional to V alpha cube, where V alpha is the velocity of the alpha particle. And we know the kinetic energy of the alpha particle. We know that kinetic energy of alpha particle is equal to half m alpha V alpha square. So here the kinetic energy of the alpha particle is directly proportional to V alpha square. That means kinetic energy of the alpha particle is directly proportional to square of its velocity, whereas range is directly proportional to cube of its velocity. Therefore, so if I combine these two, I can write the range of alpha particle is directly proportional to. So now, if a range of the alpha particle is directly proportional to e to the power of e alpha to the power of 3 by 2. Now, if I combine r alpha is proportional to v alpha cube and e alpha is proportional to v alpha cube, and you will get r alpha is proportional to e alpha to the power of 3 by 2. Or if you take the log on both sides, log r alpha is proportional to 3 by 2 log E alpha. So again, if you remove this proportionality constant, so log alpha is equal to B dash 3 by 2, or just to, this is a constant, B dash is constant, therefore you write B dash into log E alpha. Because 3 by 2 is a constant, hence the term of the energy Grigor-Neutron law can be written as, so therefore the Newton's law can be written like this. Can be written as log lambda is equal to a dash plus b dash log of E alpha. So now this is a relation between the decay constant and the energy of the alpha particle. But whereas the log lambda is equal to a plus b log r, that's a relation between the decay constant and the range of the alpha particle. And here we got the relation between r alpha is proportional to r alpha v cube, and we have e alpha is proportional to v alpha square. Therefore, if we combine these two, we'll get r alpha is proportional to e alpha power 3 by 2. And from this we conclude that log lambda is equal to a dash plus b dash log e alpha. Therefore, here the decay constant is also proportional to the energy of the alpha particle. This is about Gregor's Newton law. So now we will move on to the very important thing, the beta decay. Beta decay. We know the basic definition of beta decay. So during a radioactive decay, the dot elements having the mass number increases, atomic number increases by 1 unit, and the mass number remains same with the emission of a particle called as the beta particle. And it can be written like this: x of a to z gives rise to y of z plus 1 for a, z plus 1 to a plus e to minus 1 to 0. And this is called as beta particle. Beta particle. And this beta particle is also called as electron. That means the electron that is emitted in a beta decay is not an orbital electron. The electron is manufactured by the nucleus of the available energy. So in beta decay, nucleus either emits an electron or positron or capture one of its orbital electron. So based on that, so there are three types of beta decay: negatron or beta minus decay, negatron emission, negatron or beta minus decay, positron or beta plus decay. Then there are orbital electron capture. Then third one is orbital electron capture. That means during the emission of beta particle, it may emit either the electron or a positron, or it capture one of the orbital electron. So based on this, the beta decays are classified into three types: negatron emission or electron emission, positron emission or beta plus decay, and orbital electron capture. In all the three processes, the mass number of the parent nucleus remains unchanged, whereas the atomic number is increases by 1 unit. So now we'll see one by one. First, we will move on to the negatron or beta minus decay. I'll switch on to the next page. Negatron.
ಸ್ಕ್ರೀನ್ ಬರ್ತಾ ಇಲ್ಲ ಸರ್.
ಸ್ಕ್ರೀನ್ ಬರ್ತಾ ಇಲ್ವಾ?
ಇಲ್ಲ ಸರ್.
ಅಲ್ಲ, ಈಗ ಇಲ್ಲಿ ಒಂದು ನಿಮಿಷ. ಈಗ ಕಾಣಿಸ್ತಾ ಇಲ್ವಾ?
ಇಲ್ಲ ಸರ್.
ಹೌದಾ?
ಕಾಣ್ತಿದೆ ಸರ್.
ಅಲ್ಲ, ಕಾಣಿಸ್ತಾ ಇದೆಯಲ್ಲ, ಕರೆಕ್ಟ್ ಆಗಿ ಇದೆಯಲ್ವಾ? ನೆಗೆಟ್ರಾನ್ ಅಂತ ಅಲ್ಲಿ ಯಾರಿಗೂ ಒಬ್ರು ಕಾಣಿಸಿಲ್ಲ ಅಂದ್ರೆ ಮೋಸ್ಟ್ಲಿ ನೆಟ್ವರ್ಕ್ ಪ್ರಾಬ್ಲಮ್ ಇರ್ಬೋದು ಅಲ್ಲಿ. ಇದಕ್ಕೆ
ಈಗ
ನೆಗೆಟ್ರಾನ್
ಕಾಣಿಸ್ತಿದೆ ಸರ್.
ಕಾಣಿಸ್ತಾ ಇದೆಯಾ?
ಈಗ ಕಾಣಿಸ್ತಿದೆ ಸರ್.
ಓಕೆ ಓಕೆ, ನಾನೇನು ಚೇಂಜ್ ಮಾಡಿಲ್ಲ, ಮಿನಿಮೈಸ್ ಮಾಡಿ ಮ್ಯಾಕ್ಸಿಮಮ್ ಮಾಡಿದ್ದೀನಿ ಅಷ್ಟೇ. ಸೊ ನೆಗೆಟ್ರಾನ್ ಎಮಿಷನ್, that means beta minus decay. So these are most important questions I am explaining. So here, when a nucleus contains more number of neutrons than that of protons, if the nucleus having more number of neutrons than that of proton, it is unstable, results in an exothermic transformation in which the mass number remains unchanged and the atomic number increases by 1 unit with the emission of an electron. So that is the, so here, and it can be represented like this: x of z to a gives rise to y of z plus 1 to a with the emission of an electron. And so this is negatron. Negatron is also called as the electron. Beta minus decay. Beta minus decay. That means when a nucleus contains more number of neutrons than that of proton, so it is unstable, results in the exothermic transformation in which the mass number remains same and the atomic number increases by 1 unit. So and this can be represented like this. For example, let me take an example. Hydrogen 1 to 1 gives rise to helium 2 to 2. Sorry, this hydrogen 1 to 2. ಲೈಟ್ ಸ್ವಲ್ಪ ಹಾಕೋ ಅದೇನು ಸರಿಯಾಗಿ ಕಾಣಿಸ್ತಲ್ಲ. ಹೈಡ್ರೋಜನ್ 1 to ಸ್ವಿಚ್ ಆನ್ ದಟ್. ಓಕೆ, ಈಗ ಸ್ಕ್ರೀನ್ ಕಾಣಿಸುತ್ತಪ್ಪ ನಿಮ್ಗೆ ನೀಟಾಗಿ? ಹಲೋ
ಸರ್,
ಓಕೆ,
ಕಾಣಿಸ್ತಿದೆ ಸರ್.
hydrogen 1 to 3
ಕಾಣಿಸ್ತಿದೆ ಸರ್.
that gives rise to helium 2 to.
ಸರ್ ಬರೀತಾ ಇರೋದು ಮಾತ್ರ ಫುಲ್ ಸ್ಕ್ರೀನ್ ಮಾಡಿ ಸರ್.
ಬರೀತಾ ಇರೋದು ಫುಲ್ ಸ್ಕ್ರೀನ್ ಮಾಡ್ಬಿಡಲಾ?
ಸರ್ ಬರೀತಾ ಇರೋದು ಫುಲ್ ಸ್ಕ್ರೀನ್ ಮಾಡಿ ಸರ್.
Okay, so helium 2 to 3 plus the electron. So here the neutron can be converted into proton with the emission of electron. So neutron gives rise to proton plus the electron. Now see, this neutron can be converted into proton. So in beta minus decay, neutron can be converted into proton. So in beta minus decay, the neutron changed into proton with the subsequent emission of electron. Neutron changed into proton with the emission of electron. With the emission of electron. So now we have this equation. Say this is equation number 1. This is equation number 1. Now, so where Mn is Mn of A comma Z. A comma Z is the mass of the parent nucleus. Mass of the parent nucleus. Mn of A comma Z plus 1. So it is the mass of the nucleus Y, mass of the nucleus Y. If you apply the Einstein's mass energy relation, according to Einstein's mass energy relation, according to Einstein, E is equal to mc square. E is equal to mc square, and the energy released in beta minus decay can be written as, now you just look at the equation number 1. Equation number 1. So this equation number 1 is x of z to a gives rise to y of z plus 1 to a plus the electron. and apart from that we will have some energy. Here we can write plus Q. So therefore, this can be written as mass of A comma Z minus Mn of A comma Z plus 1 minus mass of electron into C square. So that means here you will get Q plus Q. Apart from that you will get plus Q. This plus Q is equal to, so the mass of the parent nucleus minus mass of the residual nucleus and the mass of the electron. So the mass can be converted to energy. Therefore, we multiply that with C square. According to Einstein, E is equal to mc square. Now replace the nuclear mass with atomic mass. Replace. So Mn is the nuclear mass. Nuclear mass with atomic mass. If you replace the nuclear mass with atomic mass, so Q of B minus is equal, beta minus is equal to M of A comma Z minus Zm into E. So that means the nuclear mass of the parent nucleus can be written as M of A comma Z minus E. Similarly, Mn of A comma Z plus 1 can be written as M of A comma Z plus 1 minus of Z plus 1 of Me. And you write this minus Me as it is, that multiplies C square. Therefore, Q beta minus is equal to M of A comma Z minus Z into Me minus M of A comma Z plus 1 minus, here we have Z plus 1 into Me. If you multiply, you will get minus Z into Me minus Me, and you write this minus Me as it is. So actually this becomes plus, because already we have minus here. If you multiply minus into minus plus, so here we get plus ZE plus Me into C square. So energy of beta minus decay is equal to M of A comma Z, and here we have minus Zm minus, here we have minus Zme plus Zme, that's cancelled, plus Me minus Me, that's cancelled, this gets cancelled, plus Me minus Me cancel, you will get M of A comma Z minus M of A comma Z plus 1 into C square. And in fact, if we express all this in terms of energy, the C can be ignored. In terms of energy, this is equal to M of A comma Z minus M of A comma Z plus 1. And here the condition for beta negative decay and Q is greater than Q beta minus is greater than 0. Q beta minus is greater than 0. So this is the condition for beta negative decay. If this is greater than 0, then M of A comma Z is greater than M of A comma Z plus 1. So that is required for the beta negative decay. So the final conclusion is, what is the condition required here? M of A comma Z is greater than M of, so I'll switch on to the next page. M of A comma Z is greater than M of A comma Z plus 1. So this is a condition for beta minus decay. Condition for beta minus decay or negatron emission. This is a condition for beta emission, beta minus decay or negatron emission. Next, we will move on to the positron emission or beta plus decay. Positron emission or beta plus decay. It is almost just the reversal of beta negatron emission. And here, when the nucleus has an excess of proton over that of neutron, it is unstable and results in the transformation in which the atomic number decreases by 1 unit with the emission of a positron. Whereas in case of electron emission or beta minus decay, the atomic number is increases by 1 unit, but here the atomic number is decreases by 1 unit with the emission of positron. So let me write, when a nucleus has an excess of protons, nucleus has excess of protons over that of neutrons, it is unstable. And it results in the transformation of in which the atomic number decreases by 1 unit. The atomic number decreases by 1 unit with the emission of a positron. Positron is nothing but beta plus, and the mass number remains unchanged, and it can be represented like this: x of z to a gives rise to y of z minus 1 a plus e to the power of e of plus 1 to 0, and say this equation number 1, and this is called as beta plus particle or positron. And here in a beta plus decay, a proton can be converted into electron. In beta plus decay, a proton can be converted into neutron. So, and it can be represented as so here is a proton. That can be converted to neutron with the emission of positron e plus 1 to 0, and this is called as the positron. And here also this is called as the positron. So now, when you look at the equation number 1, in the equation number 1, the x of atomic mass, the atomic mass of x is mn of a comma z, and that of y is mn of a comma z minus 1. So that means mn of a comma z is the nuclear mass of the parent nucleus. Mn of a comma z minus 1 is the nuclear mass of the residual nucleus or the daughter nucleus. So now, when a positron is emitted, the energy released in this equation is. So, and I told you this is also equal to, in the equation number 1, it's also equal to Q. Also equal to, it's plus Q plus, so Q. Now, so from the equation number 1, so Q of B is equal to, so the mass of, the nuclear mass of A comma Z, the nuclear mass of A comma Z minus Z of M into E minus of the nuclear mass of A comma Z minus 1 minus of, so then minus into minus it becomes plus Z minus 1 into ME minus ME, and this mass can be converted into energy according to E is equal to mc square. We multiply this mass with mc square. So Mn of A comma Z minus Z into ME minus Mn of A comma Z minus 1 plus Z minus 1 of ME minus of ME, and this is mass of the positron, mass of the positron, so into C square. So I'll move on to the next page. So here, if you replace the nuclear mass by the atomic mass, replace the nuclear mass with the atomic mass, so then Q of beta plus is equal to M of A comma Z minus Z into ME minus of M of A comma Z minus 1 plus of Z minus 1 into ME and minus ME into C square, or Q beta plus is equal to M of A comma Z minus Z into ME minus M of A comma Z minus 1 plus ZME minus ME minus ME into C square, and plus minus ZME plus ZME gets cancelled. Q is equal to Q beta plus is equal to M of A comma Z minus M of A comma Z minus 1 minus, here we have minus ME minus 2ME minus 2ME into C square. So after converting the mass into energy, after converting mass into energy, this beta plus decay is equal to M of A comma Z minus M of A comma Z minus 1 minus 2ME, and the condition for beta plus decay is greater than 0. If this is 0, greater than 0, then 0 is equal to, I mean, if this is greater than 0, M of A comma Z is greater than M of A comma Z plus Z minus 1 plus 2 into ME. So this is a condition for beta plus decay or positron emission. So here the beta plus decay or the positron emission is possible if the mass of the parent atom is greater than sum of the mass of the product atom and twice the electronic mass. This is the electronic mass. Mass of the parent atom, M of A comma Z. M of A comma Z is the mass of the parent atom, is greater than the mass of the daughter element and twice the electronic mass, 2 times of Me, and twice the electronic mass. So the mass of parent atom is greater than the sum of mass of the daughter nucleus and twice the electronic mass. But whereas in case of negatron emission, the mass of the parent atom is greater than the mass of the daughter element, daughter nucleus. But here, whereas in case of positron emission, the mass of the parent element is greater than the sum of the mass of the daughter element and twice the electronic mass. So that's the difference between the positron emission and the negatron emission. Next, and that means if you understand any one of these, either the positron emission and negatron emission, then it is easy to write the expression for the other thing. So next we will move on to the very important and the last thing is the orbital electron capture. Orbital electron capture. Orbital electron capture. So to study the orbital electron capture, so we need to understand the atomic structure. See, in an atom, the nucleus is at the center and the electrons are revolving around the nucleus. Electrons are revolving around the nucleus in a particular orbit. And we know the number of electrons in each orbit is 2n square. The number of electrons accommodated in each orbit is 2n square, where n is the principal quantum number. So, and this is called K shell. This is called M shell. Similar, this is called M shell. Similarly, you will get N shell. Therefore, there are 2 electrons can accommodate in the K shell and 8 electrons in the, 8 electrons in the L shell. Similarly, 18 in the M shell, so on. So now we have to find out what is meant by, we have to understand what is meant by orbital electron capture process. So I'll move on to the next page. So electron capture decay is possible if the mass of the parent atom is greater than the mass of the daughter atom. So by at least 1 electron binding energy. So this is possible only if the mass of the parent atom is greater than the mass of the daughter atom by at least 1 electron binding energy. So in the heavy nucleus, the K subshell lies very close to nucleus. I told you the K shell is very close to the nucleus. I'll show it in the diagram. The K shell is very close to the nucleus and therefore the electron captured from K shell is more probable than L and M shells. So what happens during de-excitations? The electrons in the K shell may drop down to the in the beginning, and next M shell, L shell, so on. So like that, the electron capture of K shell is more probable than L and M shells, and this type of electron capture is called K capture. Suppose if the probability of drop down electron is L is more than that of other shells, then it is called as L capture. Similarly, if the probability of drop down of electrons in M shell is more than that of other shells, that is called as M capture. So now here the probability of drop downing of electrons in K shell is more than the other shells, therefore this is called as K capture, and the electron capture process does not occur for free electrons, but the nucleus in this process can be written like this. So this is the equation for electron capture. x of z to a gives rise to, and it should have some other extra particle called electron gives rise to y of z minus 1 to a plus gamma particle, and this is called as gamma particle. And here the proton can be converted to proton plus electron converted to neutron with the emission of neutrino or the gamma particle. So consider, say this is equation number 1. Equation number 1. Consider the electron capture process and use Einstein equation here. The energy released can be written as QEC. That means the energy released in electron capture. QEC is nothing but energy released in electron capture is equal to Mn of A comma Z plus Me. So mass of, that means the nuclear mass of the parent nucleus plus the nuclear mass of the electron minus nuclear mass of A comma Z minus 1. This is daughter nucleus. This is multiplied by c square minus the binding energy. Minus the binding energy. So if you replace this nuclear mass by the atomic mass, replace nuclear mass by the atomic mass. Replace the nuclear mass by atomic mass, then the energy released in electronic capture Q is equal to M of A comma Z plus M of A comma Z minus of Z into Me, and you write this Me in the equation 1 as it is. So this Mn of A comma Z can be written as M of A comma Z minus Z into Me plus, write this Me as it is, and this minus of Mn of A comma Z minus 1 can be written as minus M of A comma Z minus 1, and minus into minus plus Z minus 1 into Me, Z minus 1 into Me into c square minus of the binding energy. Minus of binding energy. So therefore, the energy released in the electron capture Q is equal to M of A comma Z minus Z into Me plus Me minus M of A comma Z minus 1 plus Z into Me minus Me into c square minus the binding energy, or QEC is equal to, here the minus ZE plus minus ZME plus ZME gets cancelled, plus Me minus Me gets cancelled. So therefore QEC is equal to M of A comma Z minus M of A comma Z minus 1 into c square minus the binding energy. Minus the binding energy, or if you convert this mass into energy, this E square can be ignored. Therefore, the energy in the electron capture is equal to M of A comma Z minus M of A comma Z minus 1 minus the binding energy. Minus the binding energy. Therefore, the condition, if the electron binding energy B is very small, if the binding energy is very small, so is in the case of lighter atoms, this condition reduces to M of A comma Z being simply greater than M of A comma Z minus 1. That means if this binding energy is very small, so then M of A comma Z is greater than m of a comma z minus 1. Is greater than m of a comma z minus 1. So electron capture decay can occur in one and the same nucleus provided both the conditions. So under the electronic capture condition, QC is equal to m of a comma z minus m of a comma z minus 1 minus b, and this is a condition is greater than 0. Therefore, the mass of the parent nucleus is greater than the mass of the daughter nucleus plus the binding energy. This is a condition for the electron capture. The mass of the parent nucleus is greater than the mass of the daughter nucleus and the binding energy. So now you will get an idea the difference between the positron emission, electron negatron emission, and electron capture. So now if you just see the difference between the positron emission and the electron capture, in a positron is emitted by the parent nuclei, whereas in electron capture, orbital electron is captured by the nucleus and there is no particle emission. And in case of positron emission, the atomic number decreases by 1 unit, whereas in case of electron capture, atomic number decreases by 1 unit. So that's a difference. So now, and you know, the mass remains same in both the cases. So this is about the 3 different types of beta decays. So shall I conclude here?
Okay, sir.
ಏನಪ್ಪ ಏನೋ ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? ಹಲೋ ಹಲೋ
ಸರ್ ಹೇಳಿ ಸರ್.
ಹಾ ಒಂದು ನಿಮಿಷ. ಹಲೋ ಅಲ್ಲ ಏನಾದ್ರು ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ?
ಸರ್
ಅಲ್ಲ ಈಗ ನನ್ಗೆ ಸ್ಕ್ರೀನ್ ಮೇಲೆ ಬರ್ದಿರೋ ಕ್ಲೀನ್ ಆಗಿ ಕಾಣಿಸುತ್ತಾ?
ಕಾಣಿಸುತ್ತೆ ಸರ್.
ಓಕೆ ಓಕೆ. ಸೊ ನಾನು ಅದನ್ನ ಶೇರ್ ಮಾಡ್ತೀನಿ. ಓಕೆ, ಕಂಟಿನ್ಯೂ ಮಾಡ್ಲಾ? ಇನ್ನೂ 1 hour
ಸರ್.
ಇನ್ನೂ 1 hour ಕಂಟಿನ್ಯೂ ಮಾಡ್ಲಾ?
ಸರ್ ಬೇಡ ಸರ್.
ಓಕೆ. ಸೊ ನಾಳೆ ಎಷ್ಟೊತ್ತು ತಗೊಳ್ಳಿ
ಸರ್.
ಆಫ್ಲೈನ್ ನೀವು ಬರೋದೇ ಇಲ್ಲಲ್ಲಪ್ಪ. ಆಫ್ಲೈನ್ಗೆ ನೀವು ಹೇಳಿ ಎಷ್ಟೊತ್ತಿಗೆ ಅಂದ್ರೆ ಅಷ್ಟೊತ್ತಿಗೆ ತಗೊಳ್ತೀನಿ ನಾಳೆ. ಹಲೋ,
ಮಧ್ಯಾಹ್ನ ಸರ್.
ಮಧ್ಯಾಹ್ನ ಎಷ್ಟೊತ್ತಿಗೆ?
ಆಫ್ಟರ್ 1 o'clock ಸರ್.
ಆಯ್ತಾ? ನೀವು ನಾನು ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ಅಲ್ಲಿ ಇರ್ತೀನಿ, ನೀವು ಬಂದು ಕರೀರಿ ತಗೊಳ್ತೀನಿ. ಅಲ್ಲ ನೀವು ಬಂದು ಕರೀರಪ್ಪ ತಗೊಳ್ತೀನಿ. ನೀವು ಬಂದು ಕರೀರಿ ತಗೊಳ್ತೀನಿ. ಓಕೆ.
ಓಕೆ ಸರ್.